Hello. So, in this video, I am going to try and explain what the twin paradox is and why it's not actually a paradox, so that hopefully you can understand what is actually happening. So, to understand the twin paradox, there are three main things you need to know. The first is that motion is relative. Everything that moves is moving relative to something else. So, if you're in a car and you're driving down the road, you're moving relative to the road. If you're on a spaceship and you're moving away from the Earth, you're moving relative to the Earth. This allows us to pick what we're moving relative to. So if you're in your car, you might be moving 100 kilometers an hour relative to the road, but you're moving much faster than that relative to, say, the sun, because the Earth is orbiting the sun, and you're on the Earth, so you're also orbiting the sun very, very quickly. Anytime you're talking about motion, you need to specify what you are moving relative to. In any scenario where one object is moving relative to another, it's just as accurate to say the reverse and say that the other object is the one that's moving. So for instance, if you have a ship that's moving away from the Earth, you could say that actually the Earth is the one that's moving away from the ship, and the ship is just sitting there in space. You can go either way there, and this is a core part of the twin paradox. The second thing is time dilation. Basically, without getting too deep into it, the faster you go, the slower you experience time. So if you're on a spaceship and you're traveling very fast, near the speed of light, you are going to experience less time. This is why you would age less. So if you are traveling on a ship and you turn around and you come back to Earth, you will have experienced less time than the people on Earth, meaning you will have aged less. In the case of twins, you put one twin on the Earth, one twin on the ship. The twin on the ship will have aged less than the twin on Earth. The third thing is what it actually means to travel near the speed of light. When you are going near the speed of light, there isn't some universal speed limit that once you reach it, you can't go any faster. Again, everything is relative. So you might be traveling near the speed of light relative to one thing, but you might be traveling at a totally different speed relative to something else. If you are on the ship and the Earth is the one that's moving, if we say that the Earth is moving away from the ship, then when you go to return to the Earth, you are going to have to move quickly relative to the Earth, which is already moving. So you're going to have to catch up, you're going to have to match the Earth speed and then add more speed on top of that. And this is actually the solution to the twin paradox. And I have some animations that are hopefully going to make things clearer. It's still a lot of information, but hopefully things are a bit understandable. Okay, so first I want to show this animation. So this is showing the twin paradox from how we would normally think about it. So from the perspective that the Earth is stationary and the ship is the one that's moving. I just want to show what we have on the screen here. So distance is 2 light years. That means the ship's going to go 2 light years, turn around, come back, so travel 4 light years in total. The ship velocity throughout the trip is going to be 1/2 the speed of light. And then over here we have elapsed time. So how much time is going by on Earth? How much time is going by on the ship? Because remember, the ship is going to be experiencing time dilation, so time is going to be moving a little slower for the people on the ship. And then down here we have age of Earth twin according to ship twin. Now what this is going to measure is how much time the people on the ship think is passing by on Earth. And you'll see in a second what exactly that means. So remember that information can only travel at the speed of light. So what's going to happen is every year, once a year, on their birthday or something, the twin on Earth is going to send a message to the twin on the ship that he's now a year older. But of course, the twin on the ship doesn't get it right away because he's so far away. It takes time for the message to get there. So you'll notice, I'm just going to pause it for a second here. You'll notice that it takes 2 years for the twin on the ship to see that his twin back on Earth has aged 1 year. So this is why both sides of the twin paradox see the other as aging less. So the twin on Earth, if they were to get a message from the ship, they would see that the twin on the ship is aging less because less time is passing on the ship. But the twin on the ship sees that the twin on Earth is aging less, not because less time is passing on Earth, but because the messages saying that he's now a year older take so long to reach. So let's keep playing this, and we will see just what happens. So now the message saying that the twin on Earth is 2 years older is making its way to the ship, and you'll notice that the next message has already been sent because it's such a far distance that it's taking that long. So now the ship is turning around because it's traveled the 2 light years, and then at that point, so 4 years into the trip, they now see that the twin back on Earth is 2 years older. And then as he starts to head back, you'll notice that he gets the messages quicker because he's now heading into the messages. So the reason that even though the twin on the ship sees his twin back on Earth aging less, but once he gets back, he'll actually have been the one who aged less, is because of this time delay with light. So he only sees his twin as aging less as he's moving away from the Earth. Once he turns around and starts coming back toward the Earth, he starts to actually see his twin age extra quickly to kind of make up that time. So once he finally gets back to the Earth, 8 years have passed on the Earth, but only 6.93 years have passed on the ship. So then that'll be the age difference between the two twins. One twin will have aged the full 8 years. One twin will have aged, a little less than 7 years. Okay, now after seeing that animation, so that was kind of the traditional way of imagining people traveling on spaceships and then coming back to Earth. It's very clear that it's the ship that is moving and is experiencing time dilation, so the people on the ship are the ones aging less. But because all motion is relative, you can pick any reference point you want. So it's just as accurate to say that the ship is the one that's stationary and the Earth is moving away from the ship. Because, if you think about it, the people on the ship can't really tell if they're moving. They can only tell if they're moving by watching things around them. And if they look out the window, they'll see the Earth moving away from them, right? So from their perspective, it looks like the Earth is the one that's moving away. And that's just as legitimate a perspective to say that it's the Earth that's moving away. The obvious problem with that is if the Earth is the one moving, then wouldn't the Earth be the one experiencing the time dilation? So that's where the paradox comes from, because only one of them can experience the time dilation, or else there won't be the age difference. This is made up for by the fact that the ship will eventually have to speed up in order to catch the Earth again, and you'll see in a couple minutes what exactly that looks like. So first I just want to show what our conditions are here. So the distance is again 2 light years. So the ship is traveling 2 light years, except because we are talking about it from the ship's perspective, it's going to look like the Earth is the one that's traveling the 2 light years. Now the Earth velocity is going to be 0.5 c, half the speed of light. Again, because in the last example, the ship was moving at half the speed of light. So if instead we say that no, the Earth is the one moving, well then the Earth is going to be moving at 1/2 the speed of light. And that's going to cause the ship velocity to be minus 1/2 the speed of light, right? Because it's relative to the Earth, it's moving in the other direction. Over here, we have our elapsed times. We have the Earth and the ship again, but you'll notice there's an observer time. So the twin paradox, when you're talking about the perspective of the Earth being the one that's moving, is a lot easier to understand if you think about it from an outside observer. Because if you try to think about it from the perspective of the twin on Earth or the twin on the ship, things get pretty confusing pretty easily. But if you think about it from the perspective of an outside observer, then you can kind of see what's happening between the Earth and the ship relative to each other. You're not kind of stuck having to analyze the situation from within one of the reference frames. It's much easier if you're observing from the outside. So you'll see how that affects things. So the ship is not moving. So it's moving negative relative to the Earth, but that's just because the Earth is moving away. So if something's moving away from you, it's the same thing as you moving in the other direction away from it. That's all that's saying. So let's play this, and you'll notice the Earth starts moving away. And you'll notice that the Earth is in fact experiencing time dilation, because you'll notice that the time going by on Earth is less than the time going by on the ship. And you'll notice that for right now, the time on the ship and the observer time are the same because the ship's not moving. We're kind of observing the situation from the perspective of the ship not moving, so those two times are going to match for now. So you're going to notice when the Earth gets 2 light years away, the ship is going to turn around and it's going to speed up, and it's going to match speed with the Earth. So you'll notice that the Earth is going to stop. I'm just going to pause for a second. The Earth is going to stop, and then the ship is going to start moving towards the Earth. Now, the Earth isn't the one that stopped, right? It's not like the Earth had a thruster that it slowed itself down and stopped. What happened was the ship turned around to head home, just like in the last simulation where it traveled away, turned around, traveled back. In this simulation, it is, once it gets the 2 light years away from the Earth, it doesn't matter which one's at, it doesn't matter if the ship's moving or the Earth's moving. Once there's 2 light years between them, the ship is going to turn around and head back. So the first thing it has to do is match the Earth's speed. If it matches the Earth's speed, the Earth and the spaceship aren't going to be moving relative to each other. So the observer in this case is kind of moving with the system, just so that we can see it without it going off the screen. So remember, the Earth is still moving, it's just that we're showing it relative to the Earth's motion at this point, so that it doesn't go off the screen. It's not enough for the rocket to match the Earth's speed, it also has to actually reach the Earth, in which case it's going to have to go faster. But in order to go faster, it has to match the Earth's speed, and then it has to speed up on top of that. Now, in the last example, the ship was moving away at 1/2 the speed of light, and it turned around and then started coming back at 1/2 the speed of light. So the whole trip, it was traveling at 1/2 the speed of light. But in this scenario, it was just sitting there, not moving. So that means it has to kind of make up for that lost time dilation. So when it matches the Earth's speed, it's now going the 1/2 that it had to in the first animation. But now it has to go even faster on top of that, which means it's going to experience more time dilation. Speeds near the speed of light don't stack necessarily. Like 1/2 the speed of light plus 1/2 the speed of light is not, the speed of light, because you can never reach the speed of light. The faster you go, the slower time will pass for you, and that'll just keep happening forever. So if something is traveling at 1/2 the speed of light, and then it speeds up again by 1/2 the speed of light, it's actually only traveling at 0.8 times the speed of light. And that's because the time is slowing down to kind of compensate for that. So you'll now see the ship's velocity is 0.8 the speed of light, or 0.5 relative to the Earth. And you'll notice that this looks pretty much the same as the last animation, because at this point it kind of is. Since the ship is now traveling back toward the Earth, it's the kind of the same situation again. It doesn't matter that they're both moving at some speed. Since they're moving at the same speed, for this scenario, it doesn't matter, you know. They might be moving towards something else in the galaxy or whatever, but since we're only focusing on the Earth and the ship, wherever they're going doesn't actually matter. So all that matters is the relative velocity between them. And now, because the ship has to travel 0.8 c instead of 0.5 c to get back to the Earth, it's going to experience more time dilation, which is going to kind of like bring it to where it needs to be, right? So you'll notice that the observer time, a lot more time has actually passed, because since the Earth in this scenario was experiencing time dilation, that means that in order for the 8 years to go by on Earth, more than 8 years has to go by for the observer. So that's why you have the observer at 9.24. The Earth is at 8, and the ship is at that 6.93, the same as it was last time. The reason that more time was able to pass was because the ship and the Earth were both moving. The whole system was moving, right? It wasn't just that the ship was moving toward the Earth, it's that the Earth and the ship were moving. So that means they were covering distance as they were moving. So that increased the distance that the rocket had to travel on its way back. It didn't increase the distance between them. You know, they were still the same distance apart. You know, they were still 4 light years, and then they came back together at the same rate as in the last animation. But because the whole system was moving, the whole system had to travel for longer, which means more time passed. And that means that more time passed on the ship, basically catching it up to where it would have been in the other version of the scenario. Now, the point here is that both of these work out the same. So this is why the twin paradox isn't actually a paradox. The twin on Earth is always going to be the older one. The twin on the ship is always going to be the younger one. This is always going to happen. So it's kind of wrong to call it a paradox, because it's not actually a paradox. It was a paradox, you know, before it was kind of figured out. You know, it was just kind of a thought experiment. But since we know what's actually happening, it's not really a paradox. The twin on the ship is always going to be the one that ages less. The twin on the Earth is always going to be the one that ages more. Hopefully I was able to kind of make things a little clearer. It's a very hard, there's a lot of concepts here that are kind of hard to teach in a short amount of time. So I might have, you know, been too fast at some parts. I might not have explained some things well. I might have made some mistakes. It's hard to say, but hopefully my explanation along with the animations kind of makes things a little clearer. Leave your feedback in the comments if you don't mind. And if you like this video and would like to see more videos like this, or about space or physics or all that kind of stuff, that's the type of stuff I make. Like this video, subscribe, and click the bell if you want notifications. And thanks for watching.